In 1940, the following telephone conversation took place. Hello. I know why all electrons have the same charge and the same mass. Why? Because they are all the same electron that is alternately at different points in space-time. Well, in that case, positrons are the same electron, but flying from the future to the past. It would be possible to take for dialogue of two madmen, if not to know that the first madman was theoretical physicist John Archibald Wheeler, whose merit is creation of terms black hole and wormhole, and the second was his student, the brilliant Richard Feynman, one of the creators of the nuclear bomb. Thousands of books, movies, games, all about the same thing, time travel. Probably everyone has heard the phrase 100 times that the known laws of physics do not prohibit time travel. The known laws of physics before Newton, for example, did not prohibit people from flying. However, we can indeed manipulate time if we are talking about traveling into the future. For example, the more we speed up, the slower time flows for us. What's really interesting is whether such journeys are reversible. Is it possible to travel not to the future, but to the past? Einstein's theory predicted many effects that have been confirmed in practice. But you know what's truly staggering? In the late 1950s, scientists discovered tiny galactic objects the size of stars that shone brighter than all the stars in the galaxy combined. And these objects began to be discovered more and more throughout the cosmos. These objects were called quasars. Quasars fit perfectly into the general theory of relativity. A quasar is a supermassive black hole that swirls matter around it at such speeds that the matter heats up monstrously and radiates. You see, Einstein's theory, which he proposed in 1915, was already capable of describing a phenomenon discovered only half a century later. But the main point is that Einstein did not believe in a corollary of his own general theory of relativity, namely, the existence of black holes. He believed that Mother Nature will shield existence from the emergence of such objects. By the way, scientists have recently discovered quasar, which is 600 trillion times brighter than the sun. Black holes are truly so nightmarish that no one has enough imagination to even imagine how nightmarish they are. And Einstein always had a better imagination than the average man, so his disbelief is all the more understandable. One can disbelieve in the reality of time travel to the past, but it just so happens that the general theory of relativity offers various options on how it can be done. First, let's talk about the kind of time machine that most people imagine. That is, it's the kind of device where you can enter a time and place, and then you get teleported there. And everyone after that rushes to discuss the issues of emerging paradoxes. But there are other problems with such a machine that are less insurmountable, but more initial. Suppose we have created a time machine as the average person imagines it to be and are about to travel back in time, but where in the past? For example, to the last battle of the 300 Spartans in 480 BC, it seems simple. A specific time. Yes, a specific place. No, given that the Earth moves at a speed of about 30 kilometers per second around the Sun, and the Sun flies at a speed of about 220 kilometers per second around the center of the Milky Way, and the Milky Way is moving at a speed of about 550 kilometers per second, relative to the Great Attractor. Then, 2,500 years ago, at the time of that very battle planet, Earth was at a distance about 43 trillion kilometers from its current location. This case is the same as death, because to miss even a dozen meters means to be in the thickness of the Earth or to crash to death, falling from the height of the 5th floor. There is a spread of millions of kilometers, which means almost 100% probability of being in outer space. And that's only problem number one. Problem number two. Today, the nature of the terrain of the same Thermopylae so changed due to the action of volcanic forces and other natural factors that now it is completely unclear where here in general, the very same described in the history books, narrow gorge, Therefore, even traveling back in time for 100, 200 years without taking into account these corrections, you may find yourself pressed deep into some rocks. And you also have to take into account that, in the place of teleportation, there are no buildings, mounds, and animals, and so on. This is not to mention the air molecules that will be between the cells of the traveler's body, which, by the way, is no less deadly. But even if all these problems can be solved, there is still at least one more. Our own body has inertia set by the motion of the Earth at a particular moment. Therefore, during time teleportation, a hypothetical traveler will either crash to the ground or fly into space. But because of its speed, it would burn up in the atmosphere. These are just the primary problems of the very time machine, which pops up in the minds of most people when they even think about a time machine. But more or less corresponding to our knowledge of the universe, time machine, if such will be created at all, will look different. There are several designs in general, but the most pleasant will be to tell about the one that was once proposed by the great astrophysicist Igor Novikov, known also for his principle of self-consistency. He demonstrated that if the laws of physics allowed the existence of passable wormholes, then the theory of relativity allows their transformation into time machines. You have probably heard many times that tunnels through space-time. Wormholes violate the principle of causality. How does this relate to the principle of causality? Suppose that we have created a wormhole, the lower mouth of which is in orbit around a black hole, and the upper mouth is far away from it. Here is the black hole. Here is the lower mouth of the wormhole, near that black hole. And here is the upper mouth of the same wormhole, but at a distance from the black hole. Since the black hole exerts a strong gravitational attraction to the lower mouth of the wormhole, time flows slower in it than in the upper mouth. For example, since the wormhole was created, the lag has already accumulated to 1 hour, which means that the clock in the lower mouth will show 1 hour less than the clock in the upper mouth. Now pay attention. Inside the wormhole, the gravitational pull is extremely small, and according to Einstein's law of curvature, time flows at the same rate in the upper mouth of the wormhole as it does in the lower mouth. So when traveling inside the wormhole itself, you won't experience any time shift. The clocks along its entire length are synchronized. There is a time shift only outside the wormhole. Suppose the distance from mouth to mouth in the outer universe is so small that it can be traveled in 5 minutes. Then, traveling through the wormhole would take you 1 minute. Now, imagine you're near the upper mouth, and once the local clock strikes 2 o'clock, you will start traveling through the outer universe to the lower mouth and reach it in 5 minutes. So, according to the clock in the upper mouth, it is 2:05. And according to the clock in the lower mouth, since it is, as you remember, an hour behind, it is 1:05. Then you fly into the wormhole and get from the lower mouth to the upper mouth in 1 minute. Since inside the wormhole itself, I repeat, there is no space-time, warp, and the clocks throughout its volume are synchronized, you will arrive at the upper mouth at 1:06 on both clocks. Congratulations, you are at the starting point of your journey, 54 minutes ahead of your own departure. But there's one big problem. Not only are you traveling through the wormholes, but something else is traveling much faster, namely light. If it takes you 6 minutes to meet your copy, then just one quantum of light, almost immediately after creating such a wormhole, will generate so many copies of itself flying through the wormhole that the gravity they create will destroy the wormhole. That is, at the very moment when the minimum time difference between the upper and lower wormhole mouths is reached. It would seem that it is not difficult to prevent this. It is enough to shield the wormhole from photons. However, it will not be possible to fence off ultra-high-frequency quantum fluctuations of light, fluctuations that inevitably exist according to the laws of quantum physics. In 1990, Kip Thorne calculated what these fluctuations would lead to. The result was a growing explosion, and it is still unclear whether the force of such an explosion is enough to destroy the wormhole. Thorne thinks not. His friend Stephen Hawking insists otherwise. So much so that he formulated an entire hypothesis about the safety of chronology. And only the laws of quantum gravity will ever settle the debate over whether traveling back in time is possible. We look forward to hearing your thoughts, feedback, and suggestions on today's video in the comments. See you soon.